Okay, so there is a quick question that Prince could not complete because of a microphone problem. So his question is as follows: for the Netflix thumbnail problem, one of the thumbnail is the base condition and the rest are treatments. How do we decide which one to set as the base? Very nice question. So typically, whatever has been human decided, right, or whatever is the default one that they have, again, let's assume that these what do you call it, these thumbnails for some TV show existed for a while. So what they would do in such a case is whatever existed for a few days, they will use it as control and everything else as treatment. If they don't have it, then everything, they'll pick one of them randomly as control, everything else as treatment, right? Or they could go with domain experts, maybe some artists who say, hey, we should use this because we think that it might perform better than others. It's as simple as that. Cool. So let's do a quick recap as some of you have suggested. Okay, so just give me a second, please. Okay, so what we discussed in the third session was this. So we said that no test is perfect and permutation test cannot rigorously compare two distributions like this. What permutation test is comparing is some metric of these distributions like the medians. And the only as a fundamental assumption that permutation test has is that observations are exchangeable between control and treatment, which is always true for randomized trials. The beauty of permutation testing is it's super easy to experiment, super easy to play with 20 lines of code. It does not make any assumptions of underlying distributions or any complex assumptions. We have full flexibility with the test statistic. We looked at a variation where imagine we have a thumbnail or some artwork for these images. And if this is the default and if this is the new one, how do we now design a permutation test sort of setup for this? So we said what we are measuring here is a binary variable, whether something is clicked or not clicked. You have your control and treatment. All we do is simple, we shuffle all these values. So our test statistic in this case will be the difference in click-through rates between control and treatment. And we do the same thing. We permute or we shuffle all these values, compute the differences in CTRs, and then go through the same standard process that we have for permutation testing. The question is, what if we have 9 alternatives instead of 2? We can't, even if you want to assign 5% of traffic to each of them, that's almost 45% of experimentation traffic, and experiments can be risky. So we have to come up with a better strategy than this. And for that, there is a technique called as multi-arm bandits that we will discuss in this session. Then we went on to discuss about Mann-Whitney-U test, very popular test that checks if two distributions are similar or not. Very popular, very simple to understand. And the underlying assumptions of Mann-Whitney-U are that the observations from control and treatment are independent, and all the observations in control and treatment can be compared. That's the keyword. So the null hypothesis is that both control and treatment have the same distribution. Alternative hypothesis is they don't have the same distribution. And the test statistic referred by U is you're taking every pair of observations from control and treatment, and you're assigning a value of 0, half, or 0, half, or 1 based on whether control is greater than treatment or less or equal. Now, we have seen some simple examples to show that when control and treatment have the same distribution, they typically result in a U value which is equal to m into n by 2. But when control and treatment have differing values, this U statistic value deviates from this average value, which is m into n by 2. So as long as n and m are reasonably sized, this is the beauty of the test, under null hypothesis, the random variable U is normally distributed with this mean and this standard deviation. So which means, as far as our hypothesis testing is concerned, this is a null hypothesis, alternative hypothesis. We simply compute the observed U from the samples of XC and XT that we have. Then, because we know that under null hypothesis, U is normally distributed, we can plot the distribution of U because it's just Gaussian distribution with some mean and standard deviation. We can see how extreme is our observed value, from which we can get the p-values. And if the p-value that you have is, if the p-value is less than, let's say, the alpha value, which is 5%, let's assume we get a p-value of 2%. Because it is less than, if your alpha is 5% and your p-value is 2%, we reject the null hypothesis. Very simple. Now, again, please understand here that the beauty of Mann-Whitney U is we know the distribution of the test statistic, while in the case of permutation testing, we don't know that. Okay, because we know that the test statistic belongs to a Gaussian distribution. When your M and N are reasonably sized, it's much more easy, computationally much more easy to use in general. Okay, so while in the case of permutation testing, we don't have anything. So under null hypothesis, we will keep doing simulations and resamplings to compute the p-value. Okay, this Mann-Whitney U is widely used. It's non-parametric because it makes no assumptions about XC and XT. It's looking at every pair, slightly computationally expensive, but very doable. But it cannot say whether one random variable is greater or less than others. It's only testing if they're equal or not. So we discussed about the max value of the test statistic, which is M into N. And we just showed it with a simple example. And we saw some simple Python code. And the key takeaway is for the same small sized samples, the Mann-Whitney U was more powerful in avoiding type 1 and type 2 errors than the permutation test, because Mann-Whitney U is looking at all pairs. And the test statistic itself has a very nice normal distribution, while in the case of permutation, there is nothing of that sort. Okay, so as far as hypothesis testing is concerned, it's all about null hypothesis. It's about defining what is your null and alternative hypothesis, understanding the assumptions behind any test, computing the test statistic, knowing the distribution, getting the p-values, accepting or rejecting. So then there is a problem of multiple testing. If some random variable is compared with large number of random variables with the same significance level of 5%, there will be some errors in hypothesis testing, type 1 or type 2 errors, based on whether we have H0 or H1 or H0 or HA, right? Based on how we define our null hypothesis and alternative hypothesis, we'll have error. So if you're testing with a lot of these, there is a very high likelihood, especially imagine if N is 1000, there is a very high likelihood that we will come to wrong conclusions that something is statistically significant while it's not. In such a case, we should use a Hom-Bonferry correction, which basically says that you should not use the same significance level for all of them, make it more stringent. Now, another strategy is to use out-of-sample randomized tests, where we take the larger sample, break it up into two subsamples randomly, A and B. We do all of our hypothesis testing and build the hypothesis on A, while we test it on B after we come to a conclusion with A. This is very similar to train test split in whole of machine learning. Very simple, fairly powerful. Then we started understanding about confidence intervals and bootstrapping. We have not touched bootstrapping. We are taking this research paper, which is a summary of how remdesivir as a drug was used and some actual empirical data, and how confidence intervals are actually used in how actual confidence intervals are used in modern medicine, like COVID vaccine research. Okay, so we'll understand confidence interval for any metric. So this is what we were discussing a while ago.